Okay, so now we're going to go over sampling distribution for means. We went over proportions. This is for means. It's pretty much the exact same thing, just we're finding something that's a little different. Mu is the average or mean of a population, and y bar represents the means of a mean. So taking many averages and finding the average of several averages, okay? And is represented by y or y hat in our case. So in other words, the average. And the standard deviation of the mean of means, or the average of the means, is the standard deviation divided by the square root of the number of participants in our sample, okay? So here's our requirement. We've been told that pregnancies are normally distributed, and that's very important. We've been told they're normally distributed with a mean of 266 days. So they've gone and found an average here, and the standard deviation of 16 days within the pregnancies. Okay, here's our question. An obstetrician, which is someone who deals with pregnancies, is providing prenatal care, and that should say 60 pregnant women. Okay. What is the probability that the mean duration of the pregnancies will be less than 260 days? Okay, so we got to define a few things. First of all, essentially what they've told us is the average of the average is essentially what our average is. Well, we know that the mean is 266, so our y bar is going to be 266 in this case. Okay, they've also told us that the standard deviation is 16. Well, a standard deviation is represented by that is 16, okay? And that's this value here. That's not the actual calculated standard deviation. And we've also been told how many women are in this study. There's 60. So our n in this case is going to be 60, okay? And those are all the variables we really need, because this 266 is going to be our mean, standard deviation here, and n here, and we'll use that to calculate this standard deviation here, okay? So before we can even do this, we have to go over a couple assumptions here. Independence assumption. That is saying that each person's decision or each person in the study or each thing in the study doesn't affect the other. They're independent events. Well, it's probably fair to say that one woman getting pregnant, so each woman who sees this specific obstetrician, because one of them got pregnant, it doesn't mean it affected the other people to get pregnant. It's not like they maybe knew each other beforehand and decided, let's all get pregnant together. You know, we assume they're all different people and they just chose to get pregnant. They're independent of each other. Mm-hmm. So that's probably a fair assumption of these women, right? Each one event did not affect the other event. Mm-hmm. Is it randomized? Yeah, we go on an assumption that because these people are all independently got probably pregnant, that they've randomly found this obstetrician. It's not like she was specifically looking for people who would maybe have at-risk pregnancies or anything like that. We just assume it's randomized, okay? Mm-hmm. It's probably fair to assume that too. 10% condition means that we need to have less than 10% of the population. Well, there's 60 women. How many women do we think there are in the world who get pregnant?
Well, in China, there's not a lot of women.
Just in general. There's going to be billions, especially over the course of time. Even people have passed away, right? Mm-hmm. So it's probably very fair to say that 60 is very much below 10% of all the women who have ever been pregnant, mm-hmm. right? So this is a fair assumption, too. We can say that there's less than 10%. And is the sample large enough? Now, what that means is when we're looking through samples with means, sometimes we'll even have information that's skewed to the left or to the right, or have some kind of distribution like that. It turns out that if we take a large enough sample of averages, in time it will become normally distributed, okay? And that's if we have skewed data. If it's normally distributed, we don't even need that large of a sample to have a normal distribution. Okay, so this is an idea with a mean of means, or averages here, okay? They've actually told us that pregnancies are normally distributed, so it's pretty fair to say we don't even need a lot of people to say that this is a large enough sample. 60 is probably more than enough because it already is normally distributed, so it will give us a normal distribution. We'll go on that assumption, okay? You might want to read up on that idea. So anyways, we got to create our sample, or our normal distribution here. Well, we know our y bar is 266 days, and the standard deviation of y bar was equal to the standard deviation over the root of the number of people in the study. Well, our standard deviation was how many days?
266.
That wasn't.
No, 260.
The standard deviation was how many days? Yeah, it was 16 days,
sorry,
actually.
16.
That's okay. So 16 divided by everybody. And how many women were in the study? Our N.
60.
That's right, 60. So we have to calculate our new standard deviation. Our new standard deviation is the number 16, right, divided by the root of 60, which is equal to 2.065, so 2.07, we'll say. 2.07. Well, standard deviation, remember this is referring to days. So really the standard deviation of all of the averages is probably about 2.7 days, a little more than 2 days for each standard deviation. So let's quickly make our own model here to make sense of this. Okay. We know that the middle of this model is going to be how many days?
16.
Actually, no, we're talking about how long a pregnancy is. Well, the middle of this is going to be the mean of all of the means. So the 266. That's going to be our average. Okay, and then we're going to talk about how all these averages deviate. Each of these averages will deviate. We'll have 1 deviation to the right, 1 to the left, 2 to the right, 2 to the left, and 3 to the right, and 3 to the left, okay? And we're just going to figure out what these values are. So I'm going to say plus 1, plus 3, and minus 1, minus 2, and minus 3. So that's 268.7, right? Mm-hmm. This one will be 270. Oh no, 0.07. This will be 270.14, I think. Mm-hmm. And this one will be 272.21 days. Mm-hmm. Going the other way, you might have to help me out a bit. I think this will be 263.93.
Yep.
And then
261.86.
Thanks. 259.79. Great. Okay. In other words, these are all days, so we can. It's not exact, but we can almost say, this is about 268, 270, 272. We're pretty close to those ideas. And 263, 261, and 259. Okay, so the real question asked us, right, is what's the probability that the average, so of these 60 women, that their average pregnancy, so the average of all of them, will be less than 260 days? Well, 260 days, in this case, falls somewhere in here, right? It's going to be between the two of them, our 260 days. And they're looking for less than 260. So we're going to have to find that z-score in order to figure this out. Now, the z-score for this is going to be our data, which is our y here, subtracted by the average, and our average in this case is going to be our kind of y hat, divided by the standard deviation of y bar, okay? And again, that's very similar to our x, subtract x bar, divided by standard deviation, okay? Well, our y here in this case is our 260. We want to know how many are less than 260 days. So z is equal to 260. The average, our y bar, was 266, divided by our standard deviation was 2.07. 2.07. So the z-score of this is 260, subtract 266, divided by 2.07, negative 2.89. I'm going to say negative 2.89. What was it? Negative 2.899, was it? Or was it 989? I might have read that wrong. Hold on. 2.898. Okay. You can almost say this is negative 2.9 almost. So let's go with that. We'll go up to the roundup. So it's a z-score of negative 2.9. That's actually pretty extreme in our z-score. So I can get you to take a look at that, right? Because that's almost 3 deviations away from the mean. Okay, in this case.
Okay.
So, it's okay, don't rush. I'm just going to draw it out again. Remember that 3 deviations from the mean deals with like 99.7%, right? So the likelihood of this is going to be very, very small when we look up our z-score.
0.0019.
0.0019?
Yeah.
Okay, so as a percentage, that's literally 0.19%. Okay, not even 1%. It's extremely unlikely that the average of these pregnancies will be less than 260 days.
Wow.
That'd be very, very rare that the average. Now, we're not saying that one of the pregnancies might be less than 260. That is probably plausible because individual data varies more. But averages of groups, the average of the group of women for all, essentially saying that almost all of these women's pregnancies are kind of less than that, is very unlikely. Okay, so the idea that the average of them will be less than 260 is an unlikely event from what we've discovered.